I'm going to give maybe about 5 minutes of background, so that what I'm about to say makes a little bit of sense. Now, you guys know that when you calculate probabilities, you're basically looking at, when you look at a probability, right, probability of A, you're looking at the percentage and number of outcomes that satisfy your criteria over the number of possible outcomes, or the percentage of them, right? So, in other words, when we looked at what's the probability that we would get two heads, we tossed a coin 3 times, that we would get two heads. That's the outcome. Well, they were equal probabilities. Each outcome was 50% heads or tails. So on the first coin toss, probability getting heads or tails, both 0.5. On the second coin toss, probability of getting another head is 0.5 and another tail is 0.5, right? Independent events, that's another, 0.5. That's another head and another tail, right? Or if we had a tail on the first one, same deal. Probability getting a head on the next one is 0.5. Probability of getting a tail is 0.5. And then again, next group, right? Heads, tails, going to be 0.5 again. Tails, 0.5. Heads, tails. 0.5, heads, tails. And finally, heads, tails, right? And we figured out that all of these are equal probabilities because they're all 50-50 shot after you, and they're independent events. So probability of getting 3 heads is 0.5 times 0.5 times 0.5, which is equal to 0.125, right? That's 3 heads. Probably the next one is going to be heads, and tails, right? That's 2 heads, is going to be 0.125. Let's see, heads, tails, and then heads, that's 2 heads, is going to be 0.125. Heads, tails, and tails, that's 1 head, is going to be 1.125. And I keep going. Now the first one is tails, heads. Heads is going to be 2 heads, 0.125. 0.125. Heads. Tails, tails, heads, tails is going to be 1 head, 0.125. Tails, is going to be 0.125. That's 0 heads. Okay, so how many possibilities are there? Well, there's 8. I might have missed one. I don't know. I think I might have missed one here somewhere. What is this? Tails. That one. That was 1 head. I think there might have been another 1 head here also. Okay, so all of these 0.125. Okay, so there are 8 possibilities. They add up to 1 if you add up all of these, right? Probability of getting 2 heads is there's 1, 2, 3 ways of doing it. So it's 3 over the 8 possibilities. That simple, right? So now things get a little bit more complicated when it's not equal probabilities. Let me get a new page. Okay. If we have a couple of answers to test questions, right? Let's say that the probability of the first question, getting the first question right, correct, incorrect. Probability of getting the first one correct is 80%. Probability of getting incorrect is 20%. That's the rate at which people tend to get that question correct. Now, after you've answered that first question, second question is completely unrelated. Probability of getting second question correct is 50%. Could get 50-50 chance of getting it correct or incorrect, right? And same thing here, correct or incorrect, 50% and 50%. Okay, so what's the probability of getting 2 correct answers? Well, let's see, 0.8 times 0.5 is 0.40. That's 2 correct answers. Well, how about this possibility? Correct, incorrect. Well, that's 1 correct answer. Probability of that occurring is 0.8 times 0.5 is 0.40. Now, the probability of this going this direction, getting that first question incorrect, getting the second question correct, one correct answer, but getting the first one incorrect is zero point 0.2 times 0.1, which is 0.5, which is 0.10. And finally, the probability of getting both of them incorrect, no correct answers, is 0.2 times 0.2, which is 0.10. So this represents all of the possibilities. In fact, if you add it up, you see it adds up to 1.0. Okay, so what's the probability of getting two correct answers? The probability of getting two correct answers is 40%. What's the probability of getting one correct answer? Well, there's two ways for that to happen. So the probability is additive here. So it's 50% chance of getting only one correct answer. And there's 10% chance of getting none correct. Okay, if you randomly pick someone's performance on this test. Okay, so now one of the things that you can say to yourself is, what's the probability of getting the second question right, given that you got the first answer right? Well, the probability of that happening, well, it's 50%. Probability of getting the second question right, because now that this has occurred, it's taken out of the mix. So we're only concerned really about the probability of getting the second one right within this population. So that's kind of a conditional probability. But we're going to look at special conditional probability that has to do with diagnostic testing, because that's most often how we're going to apply Bayes' theorem. Okay, so now I'm going to get another page here, and I'm going to reprint out I'm going to redo that page that we started with. We started with a test that had a sensitivity of 80%. It had a specificity of 90%, and there was a condition where the prevalence was 20% in the population. Okay, so I'm going to set up a box here. Okay, and I'm going to say I'm going to start off with 1,000 people. Okay, so the prevalence is 20%. Out of that 1,000 people, 200 people have the condition. So the way I'm going to lay out this box is, these are the people that have the disease. These are the people that don't have the disease. These are the people that test positive. These are the people that test negative. So 20% of them have the disease. That means 200 out of 1,000 have the disease, and 800 don't have the disease. So anybody in this column doesn't have the disease. Anybody here does have the disease. Well, the specificity tells me what percentage of the time will correctly identify people with the disease. That's 80% of the time. So in other words, we will get a positive test for these 200 people 80% of the time. In other words, we'll correctly identify 160 people as having the disease. Well, that means we're going to miss 40 people. They'll test negative even though they're in this column and have the disease. How about people that don't have the disease? Well, 90% of the time, we're going to correctly identify they don't have the disease. 800 people don't have the disease. 90% of them would be 720. So that means 80 of those 800 people, we're going to incorrectly get a positive test even though they don't have the disease. So if I look now and I say to myself, what's the total number of people that tested positive in this population? It would be 160 because they had the disease and were correctly identified, and 80 because they were false positives. They were people that tested positive even though they didn't have the disease. That adds up to 240. So if I ask you, what's the probability of having the disease? Well, that's just our prevalence. What's the probability of testing positive? What's the probability of having the disease given that you have tested positive? Probably having the disease given that you've tested. Well, these are the people that have tested positive. What's the probability that they have the disease? Well, 160 out of the 240 that tested positive have the disease. Right? That is our positive predictive value. That's the percentage of the time that our test, a positive test, is right. So 67% of the time, you have the disease if you tested positive. 33% of the time, it's wrong. The test is wrong, and you don't have the disease. That's our positive predictive value. That is a conditional probability, right? It's the probability you have the disease given that you test positive. It completely ignores the 760 people that don't have the disease. They're not even part of this consideration. Okay, so now I'm going to set up a decision tree for this box. Okay, so let's see. My decision tree is going to be, let's see, people in this box, right? Probability, people in this box, they have the disease and they test positive, right? They both have the disease and they test positive. Okay. People in this box, right? They let's see. I'm gonna lay this out a slightly different way. Tell you what, let me erase this bottom part over here so I got a little room to work. There's my eraser here. I know I got one here somewhere. Maybe there's tools. I gotta have a way to erase this. Well, maybe I just can't use this a little bit wider. Okay, maybe we can get away with it down here. Okay, so I'm gonna look at this. I'm gonna make a decision tree just like I did before. First thing is, do you have the disease or do you not have the disease? Okay, so let's see. We have start out here, and first thing, a decision we make: do you have the disease? Are you disease positive or disease negative? Well, the prevalence is 20%. 20% of the people, if you pick somebody at random, 20% chance he has the disease, and there's a 80% chance that he doesn't have the disease. Okay, so now out of those people, what's the probability that you test positive? Well, if you have the disease, test positive, test negative. If you have the disease, the sensitivity says that 80% of the time you're going to test positive. So this is going to be 80%. This is going to be 20%. You're going to 20% of the time you're going to test negative. If you don't have the disease, right? Well, 90% of the time you're going to test negative, and 10% of the time you're going to test positive. So let's see. The probability of testing positive and having the disease is 0.2 times 80 is equal to 0.16. In other words, disease and test positive is going to be 0.16. Okay, have the disease and test negative is going to be 0.2 times point times 0.2 is going to be 0.04. Okay, that's have the disease and test negative. Okay, how about not have the disease and test positive? Not have the disease and test positive is going to be 80%, 0.8 times 0.1 is going to be 8%. Not have the disease and test positive is going to be happen 8% of the time. And then have the disease and test negative, 0.8 times 0.9 is going to be negative disease, negative test is going to be 0.8 times, it's going to be let's see, 0.72. And if I add all this together, what does it add up to? It adds up to 1.0. That's all the possibilities. Let's think about our positive predictive value. What's the probability that you have the disease given that you've tested positive, right? Well, first of all, the people on top of our ratio are going to be the proportion of people that satisfy our condition. They had the disease and tested positive, right? So let's see. The people on top, people that tested positive, is 0.16. Out of all of the people, all of the possibilities, that's the people that tested positive. Who tested positive? 16% of this outcome tested positive, and this outcome accounted for 8% of the time tested positive. So the sum of those two is 0.24. So the probability you tested that if you have the disease, given that you've tested positive, is 0.16 over 0.24, or 2/3. Just like our 0.67 that we calculated before. Okay, let's take this one step further. Bayes' formula. Okay, and I'm going to see, do I still have it here? Let me see. Let me hit escape here. Okay. All right. Hopefully I haven't lost you too much. You can go back and go over this again. Let me see. Let me see. No, 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 no. Okay, here's Bayes' formula. Probability of A given B is equal to probability of B given A. Let me open a new page. I'm going to recopy that. Okay. Probability of A given that B has occurred is equal to the probability of B given that A has occurred times the probability of A. Okay? Over the probability of B. Let's think about this. Let's say that for our purposes, we're looking at the conditional probability, the positive predictive value. The probability that person has the disease given that they've tested positive, just as we did before. That's going to be equal to the probability of B, which is testing positive, right? Given that they, let's see, A is going to be that they have the disease, okay? Times the probability, what is A again? A is that they have the disease, right? Probability that they test positive given that they have the disease, that's our sensitivity. 80% of the time they're going to test positive if they have the disease. So that's 80% of 0.8, and probability they have the disease, that's our prevalence, and our prevalence is 0.20. So this is our sensitivity, and this is our prevalence, right? So let's take a look at the bottom of this formula now. So now we have to look at all the conditions where you would get a positive test. This is the place where you get the positive tests that satisfy you. In other words, they tested positive and have the disease. This is where all of the tests are accumulated where they tested positive. In other words, when they tested positive and had the disease, and tested positive and didn't have the disease, just as we had done before. Okay, so let's figure this out. What are we going to put down here? Well, if we go back to our decision tree, right? Go back to our decision tree. Here's our decision tree. Let's see. What are the places where they tested positive? One place they tested positive was the same as the top. In other words, they tested positive. Oops. I'm getting mixed up here. Bouncing between these two. That's my decision tree. Okay. What? Oh, I know what I did. Wrong direction. Nope. Where'd my page go? Eek. Yeah, I got to neaten this stuff up. Was it over here? Can I do it over here? Nope, that's too far. Where did I put it? Do I have a third page open here? Yeah, I have a third page open. That's what happened. Okay. All right, so now, let's see. Now, if I go back here, I have to get back to the page I was working on. Where did that go? Bayes notes, untitled, another untitled. Here it is. There we go. If I go back here, well, there's two conditions. This is where they had the disease and tested positive, right? Which satisfies our condition. Down here is all of the cases where they tested positive. And one of those cases is going to be just what's up here. In other words, the probability they had the disease, right? Probability they tested positive and had the disease, times in other words, the sensitivity times the prevalence, right? That's one way we can get a positive test, right? And that again is the sensitivity times the prevalence. But we can also get a positive test among the people that tested positive and didn't have the disease. Well, who are they? They are these people. They are, where are they? Where did I put them now? They are the people that tested positive but didn't have the disease. And who were those people? Those people were the 0.8 times the 0.1. Well, where did that come from? The 0.8 is the inverse of the prevalence. In other words, it's 1 minus the prevalence, 0.2 subtracted from 1. That's the 80% of the people that don't have the disease. So it's 1 minus the prevalence times the 0.1, which is ones that tested positive. And what is that 0.1? That 0.1 is 1 minus the specificity. So this part of the equation is going to be, and let me try and get back to it again. This part of the equation is going to be, we're going to add to these probabilities the 1 minus the prevalence times 1 minus the specificity, which is going to be, let's see if I actually work that out. That's that's actually going to be over here. We have our 0.8 times 0.20 plus, and this is going to, prevalence is 1 minus the prevalence is going to be, let's see, what's that going to be? 1 minus prevalence is going to be 0.80 times 1 minus specificity is going to be 0.10. Okay, so on top, we have 0.8 times 0.2, which is equal to 0.16. And on the bottom, we have 0.16 plus 0.08. Or in other words, some of that's 0.24, which is equal to our 2/3. Same answer we got before. So another way that we could express Bayes' formula, where we're talking about positive predictive value, probability that you have the disease, given that you test positive. Another way of expressing that, rather than this P given A, B, and so on and so forth, is to express it as saying it's going to be equal to the sensitivity. And you can actually use this on the test. If we give you sensitivity, prevalence, and specificity, you can actually use this. Sensitivity times the prevalence divided by the sensitivity times the prevalence plus 1 minus the specificity times 1 minus the prevalence. And you can actually use this formula to calculate the positive predictive value instead of actually, trying to set up that table and go through that whole exercise. Okay, so